My name is Alan Monaghan. I'm the mission coordinator for the Net Zero Industries mission, and I would like to welcome you all to the latest of our webinar program in industrial decarbonisation. This one is on hydrogen pathways, scaling the value chain for a net zero industry, and we're holding this webinar in collaboration with some of our major partners, including AFID, the Clean Hydrogen Mission for Mission Innovation, the CETP, and of course IRENA being the main sponsors of the Alliance for Industry Decarbonisation, or AFID. It is my pleasure to introduce your welcoming representative of the Net Zero Industries mission, our mission director, Mr. Urban Piker. Urban is the mission director of the mission, of course, representing our co-lead nation of Austria. He is currently the head of industry, enterprise and financing department at Austria's Climate and Energy Fund, and brings to the role extensive experience in industrial transformation, clean energy and financing. Urban, over to you, my friend.
Thanks a lot, Alan. Hi, it's my great pleasure to welcome you to today's webinar. It's part of the Net Zero Industries series. Thank you all for joining from across the globe. It's a large audience. It's a truly international audience. We are really truly delighted to have you here. Once again, it is a special webinar, as you will not only get insights into cutting-edge hydrogen projects and initiatives, and will hopefully get answers to questions around scaling the hydrogen industry. It is, and Alan mentioned it already, it is a special one because we are co-hosting it with friends and family, if you allow me to say so. We are delighted to co-host this webinar with our long-standing partners, the Alliance for Industry Decarbonisation, AFID, an alliance that has truly created impact in accelerating the decarbonisation of industrial value chains. And on the other hand, our second co-host partner for today is the Clean Energy Transition Partnership. Over the past years, they have provided substantial support in funding crucial transnational projects that support various dimensions of the energy transitions. Both ends of the value chain are hence covered, and to make the picture complete, I'm very happy that Piero Venturi, Mission Director of the Clean Hydrogen Mission, will kick us off with his keynote. Before I hand over to our co-hosts for their welcome note, let me briefly allow me to introduce our mission to you, and I think we have prepared at least 2 slides for that. If we can move to the next slide. Is that possible? Otherwise, I keep on talking and maybe the slides will change soon. So our mission, which is the Net Zero Industries mission, is a global initiative under Mission Innovation, and it's focused on speeding up transition of energy-intensive industries such as cement, steel and chemicals to net zero carbon emissions. These sectors are fundamental to our economies and are responsible for roughly a quarter of global greenhouse gas emissions. Transforming them is therefore critical to meeting our climate objectives, but as well to maintaining a vital source of economic prosperity. Cutting emissions in these sectors and industries is especially demanding due to their complexity and significant investments required. And while many breakthrough technologies already exist, they still need to be scaled and commercialized. Thanks a lot for sharing the slides now. Our ambition is to deliver 50 large-scale demonstration projects across energy-intensive sectors, testing a range of technology pathways. We support fast-track development and breakthrough low-emission solutions, help them to progress to higher technology readiness levels, and by the same time, lowering capital expenditure. A central purpose of hosting these webinars is to facilitate knowledge sharing and showcase innovation solutions that enable net zero transition. Building knowledge is essential to strengthening trust in emerging technologies. Establishing trust in these technologies is a prerequisite for anything else that follows, which is the reason why we all gather here. I'm really very much looking forward to the presentations, to the projects, and as well to the discussions. And with that, I'd like to hand over to Alan Monaghan, who will once again be our moderator today in his role as our mission coordinator.
Thank you, Evan. Our next speaker is Zafar Samadov. He's the head of partnerships at IRENA and the head of the Alliance for Industry Decarbonisation. Zafar advances partnerships with international, regional and national stakeholders, along with the industry sharing of common vision of promoting an accelerated deployment of renewable energy and net zero ambitions. He leads the multi-stakeholder platforms, the Alliance for Industry Decarbonisation and the Utilities for Net Zero Alliance. Zafar, please take the stage.
Thank you, Alan, and good morning, good afternoon to you all. I'm very much pleased also to be part of this webinar, and thank you for the all to organizing partners. I want to share with you a few views of the agency and the AFID when it comes to green hydrogen. According to IRENA analysis, the global energy transition is progressing, but remains off track to meet the 1.5 goal. That underscores the need for urgent acceleration and structural transformation across energy and industrial sectors. Renewable-based fuels, particularly green hydrogen and its products, derivatives, are essential for decarbonizing hard-to-abate industries, an application where especially electrification is not technically possible. Scaling these solutions would require infrastructure, manufacturing, and skills. I would like to share with you the few views of the industry that published a report on the hydrogen hubs that illustrate that a lot needs to be done to develop the value chain for the green hydrogen. We need to integrate production, storage, transport, and use, which all will together provide a structured pathway to the scale renewable hydrogen market. It all depends on how we can align the renewable power production, transport, supporting infrastructure, and also importantly, demand for the hydrogen. Of course, technology alone is not able to deliver on scale. We need also enabling conditions like supportive policies, financing framework, skilled workforces, and also people, communities, acceptance, which are essential to unlock investment and deployment. The analysis of the AFID also underscores the importance of early anchor demand from the major industrial users to send clear market signals to the industry and catalyze the value chain. Altogether, these insights and views of the industry provide a clear viewpoints and conclusions. Scaling green hydrogen is not only a technological challenge, but also one of the system integration and coordination. Success will depend on many factors, aligning policy, infrastructure, finance, industrial actions across different sectors, and the borders as well across the countries. Platforms like this webinar and other collaboration platforms like AFID provide an important place for the industry, governments, different stakeholders to foster joint action, align, and translate our ambition into implementation. So with this one, I would like also to thank you all for joining this webinar, and I look forward to our discussions today. Back to you, Alan.
Thank you, Zafar. Our next welcome introduction is from our partner, the CET Partnership. Can I please introduce you Asa Bergeras Vensvik, Research Program Manager from the Swedish Energy Agency. Asa is a research program manager and oversees RD&I funding for programs and projects focused on sustainable industry and international collaboration. She leads the Clean Energy Transition Partnerships TRI 6 for the focus area of integrated industrial energy systems. Asa, please, over to you.
Thank you. Sorry about that. I will share my screen. I have a presentation. We are very happy to be part of this collaboration, and I will introduce you a little bit to Clean Energy Transition Partnership, CETP. So this is an initiative co-funded by the European Union that brings together public and private stakeholders from European and non-European countries and regions. CET partnership aims to contribute to the EU goal of becoming the first climate neutral continent by 2050. And we have annual transnational research and innovation joint calls. And we also work to boost peer-to-peer learning and impact maximization by knowledge community and impact networking. So there are 23 EU member states and 10 associated countries. And there are about 50 plus funding partners. And we also are co-funded by the European Commission. And we have 13 coordination units, and we have annual calls with the budget in order of 100 million euros each year until 2027. And right now we have 108 ongoing projects, and our call 2024 with 55 projects are starting right now. And from call 2025, we have 121 projects coming to the second stage of the proposal. So CET partnership is organized in 7 transition initiatives, so-called TRIs, which are the thematic configuration of the partnership. Each of the TRIs is led by one of the CET partnership partners, known as a TRI lead, and each TRI defines the scope of one or more core modules. And the core module defines the topics of each annual joint call. So all involved funding partners then decide which core module they wish to participate in. So note that not all funding partners participate in all core modules. So for this webinar, I would say that core module 4, industrial carbon management, core module 5, hydrogen and renewable fuels, and core module 9, integrated industrial energy systems, are the most interesting for you. So core module 4, TRI 3 is leading core module 4, industrial carbon management, which is development of CCUS technologies to accelerate the decarbonization and achieve climate neutrality. They focus on reducing cost, enhancing scalability, and enabling the industrial deployment of CCUS technologies. And of course, the core module 5, hydrogen and renewable fuels. Acceleration of hydrogen and renewable fuel technologies to meet EU climate goals. It focuses on clean production, distribution, storage, and end-use technologies that will help replace fossil fuels and reduce CO2 emissions. So core module 9 for industrial energy system is a joint call between TRI 6 and with NIM. And the goals is to enabling resource efficient industrial energy systems towards climate neutral industry, enabling by increasing use of renewables like green hydrogen and its derivatives, and enabling renewable energy integration with industrial flexibility. So the CET partnership joint call will be available on our website in the end of May, and we are planning call launch in May, and the opening of proposal submission will be in June, and deadline for pre-proposal submission will be in October. So that's all from me. Thank you, and don't hesitate to reach out if you have any questions, either to me or to Age Sangeland, who are the lead for TRI 3. And of course, we have the website and LinkedIn and YouTube and B2Match in CET partnership. That's all. Back to you, Alan. Thank you.
Thank you, Asa. In my experience, people who provide funding are always very, very popular. So it's good you put your contacts there. Now we're moving on to the presentation part of the webinar. And it's my pleasure to introduce you to Piero Venturi, who's the Clean Hydrogen Mission Director who works with the European Commission. He's worked there for nearly 20 years in food, agriculture, bioeconomy, energy and international cooperation with a focus on Latin America and Africa. Piero, over to you, please.
Many thanks, Alan, and many thanks also to Urban, Zafar, and Asa for organizing this important event and also for inviting me. So The title of my presentation is Hydrogen Integration in Hard-to-Abate Sectors, Opportunities and Barrier. And in the next slides, you'll see a very quick overview about the subject I'm going to touch in the next 9 minutes. Let's start with a short presentation of clean hydrogen mission. In next slides, you see that the mission is one of the 7 missions of mission innovation. The goal is very clear. The clean hydrogen mission is a catalyzer of international activities in research and innovation with the aim to develop a global clean hydrogen value chain. Our ambition is to establish in different hydrogen valleys that can work synergetically all over the world with a special focus on emerging and developing countries, aiming to build up a strong global hydrogen economy. We have 21 member states. I would like to mention the co-leads that are the European Commission, Spain, UK, Chile, US, and Australia, and we have a strong cooperation with key international partners as UNIDO, as IPHE, Clean Hydrogen Partnership, and the Hydrogen Europe Research. In the next slide, I'm going to give you an overview about the state of play for fossil hydrogen and low emission hydrogen. Well, following the data of the Global Hydrogen Review produced last year from the International Energy Agency, we see that the global hydrogen production reached almost 100 megaton in 2024. And this is very largely produced out of fossil fuel. The main countries involved are China, with a total of 30% of the production, followed by Northern America and the Middle East, while other significant productions are reached in India and Europe. We have to take into account that at present production remain mainly in loco, and the international trade is very poor, very minimal. It's important also to consider that the fossil fuel pathway for hydrogen production is generating almost 1 gigaton of CO2 last year. This is roughly 2% of the total CO2 produced at the global level. So we can say that hydrogen demand is dominated by traditional sectors, refining, ammonia, methanol, and fossil-based direct reduced iron, while new applications account for less than 1% of the demand. In the next slide, you can see the production. They have some data on the production of low-emission hydrogen that reached almost 0.8 megaton, mainly from fossil-based combined with CCUS and electrolysis. Also taking into account that biomass to hydrogen and methane pyrolysis plants also contribute but remain very marginal. Always following the projection of the Global Hydrogen Review, we see that theoretically low emission hydrogen production could increase even to 37 megaton per year based on projects that are announced. However, real numbers are smaller, with only 4.2 megaton per year operational, under construction, or reached through final investment decision. It's also mentioned that if we would have supportive conditions, it's estimated that, like for example, cost gap, close demand stimulated, and infrastructure developed, we could add an additional 6 megaton produced, leading to 10 megaton volume total. Unfortunately, we have to say that several early stage projects have failed due to legal, economical, and technical challenges. In the next slide, you can see the situation concerning offtakes. Offtake is lowered in 2024, and only 20% of the offtakes signed in 2024 are firm agreements. So we can say that generally traditional applications as ammonia and refining declined, while agreements related to new applications, steel, aviation, shipping, and power generation, increased, with shipping accounting for even half of all agreement. Well, if we consider the total volume since early 2020, so roughly 6 years, we can say that we reach more than 6 megaton a year by end of 2024. But in the reality, firm agreements only represent 1.6 megaton a year. And these are activities that are concentrated in Europe with around 50% of all volume, then followed by Japan, Canada, and US. In the next slide, we see that in the moment where there was when the low emission hydrogen was perceived a kind of a silver bullet available for all projects, it was seen as a solution for decarbonizing energy, transport, and the industry. In the reality, what is going to happen at present is that for what concern the road transport sector, we have a use of hydrogen only for heavy good vehicles, and this is happening mainly in China, while energy applications remain very limited and concentrated specifically in Japan and South Korea. We have chemicals and refining that are still considered as an option, and applications as shipping, aviation, steel, fertilizers are emerging and are becoming more important. Next slide. We see where are the main challenges. Well, obviously, we see that the demand for low emissions hydrogen remain very low, and this is far below the expected production output by 2030. We feel that there are initiatives by governments and private actors, but they are still very fragmented. They are progressing very slowly, and there are not significant results. A big issue is the cost gap between low emission hydrogen and fossil hydrogen. This is perceived as a major barrier. Clean Hydrogen Mission had a survey among its members, and the main barriers were clearly identified, and mainly long permit and approval procedures, slow rollout of renewable sources, lack of skilled forces and workforce, and supportive policies and regulation. Finally, my last slide is mentioning our strategy, that the mission strategy for 2026 that is adapted, placing demand at the heart of our work, and is adapted to take into account in our 3 pillars. So research and innovation, hydrogen valleys and demonstration, policy enabling environment. So what we want to do is, on the first point, accelerate R&D by enhancing dissemination of technology development for end use. On the second one, we want to support our partner of the Clean Hydrogen Partnership on their Hydrogen Valley platform, setting up essential cooperation. And on the third point, we want to really to create synergies to develop policies, regulation, and training programs with all our key partners. That's it. Thanks a lot.
Thank you, Piero. Remember, everyone, please put your questions into the chat, and we will be having a dedicated Q&A session for all of our speakers at the end of the presentations. Next, if I could please introduce Benji Lee. He's a strategic policy advisor at the HILT, the Heavy Industry Low Carbon Transition CRC in Australia. Benji specialises in energy and climate policy development, future fuels research, and net zero carbon strategies. Today, he's talking about de-risking decarbonisation and the hydrogen policies in Australia. Benji, over to you, my friend.
Thank you very much, Alan. I'll just get this presentation under control. Thank you. I'm going to be giving, I guess, a bit of insight into hydrogen policy development in Australia. And yeah, the organisation I represent is HILT CRC, which stands for Heavy Industry Low Carbon Transition Cooperative Research Centre. Just a bit of a overview of the many different things that HILT CRC touch on. We're a collaborative research centre made up of heavy industry, government, technology providers and universities. We focus on iron and steel decarbonisation, alumina decarbonisation, and cement decarbonisation. You'll see from the screen that we're involved with most of, I guess, the big heavy industry players in iron and steel and alumina, particularly. In the Pilbara, which is obviously a big iron producing part of the country. Also Kinana and Southwest, which is more alumina and other heavy industry. The Upper Spencer Gulf, which includes Whyalla, which is a South Australian magnetite and steel producing sort of region. Up in Queensland, Gladstone, which is a big exporter of gas, but also has some alumina and other heavy industry. BlueScope, which is a major steel producer of Australia, based in New South Wales, and where I'm based in Melbourne, but originally I come from northern Tasmania, and there's also magnetite production down the tiny little island on the bottom there. You'll see on this slide there's also a number of different international partners. Just a call out to Net Zero's industry mission, which logo's up the top. HILT CRC actually facilitates Australia's co-leadership of NIM, and we're very proud to do so, and we're very thankful for the opportunity to speak today. Lots going on here in this slide, but I just wanted to sort of, I guess, bring to attention that there's, I guess, lots of technology and lots of energy related research projects that HILT CRC get involved in. I guess some of the things that are more of relevance to what I'm talking about today are the green coloured projects, which are very much focused on transformation and or policy, and project techno-economics, that sort of thing. Now, in terms of Australia's national hydrogen strategy, the most recent strategy was in 2024. Like Piero was saying, there was a bit of a rationalisation. Australia's first national hydrogen strategy in 2019 was very much focusing on exploring out all the many different potential uses of hydrogen. And I guess the thing to sort of call out in the 2024 strategy was really a much stronger focus on heavy industry abatement, and also hydrogen hub formation. But I'll just get on to, I guess, stepping through some of the key policy mechanisms that are in play, I guess, trying to incentivise hydrogen in Australia. One of the key ones, and it's now under consideration, is the Hydrogen Head Start Round 2 program, 2 billion Australian dollars as part of that funding round. It links closely in with the hydrogen production tax incentive arrangements. Interestingly, in the Hydrogen Head Start Round 1 version, that was undersubscribed. That was also a $2 billion fund, and I think about 1.24 billion was devoted to 2 major projects. Where things are going with this latest round is, I guess, getting more price discovery around what that production tax credit, so I guess the dollars per kilogram of hydrogen over a 10-year period that will be needed to actually get projects going and built, because at the moment there's a real need for that to happen, and only very small projects at the moment have happened in Australia, around the 2.5 megawatt electrolyzers, with a couple of 10 megawatt ones sort of being built at the moment. The Guarantee of Origin scheme, a real key one. The Hydrogen Go, as it's called, has been put in place. On the back of that now, we've got an alumina one under consultation. And then we're told alumina, iron and low carbon liquid fuels will follow pretty soon throughout the rest of this year. And I guess that's why I'm mentioning that it's really starting to now leverage off hydrogen into sort of industrial policy. There's a $5 billion net zero fund, which has been released from the $15 billion National Reconstruction Fund Corporation. Recently, they've just relaxed their return expectations. So it's quite attractive, I guess, for innovation scale up. So that has been good to see. A $1 billion green iron investment fund was also opened. And what I guess industry here are very much sort of looking at the moment is the review of the safeguard mechanism. And that's, I guess, a policy that imposes, I guess, a carbon price on just the heavy, big emitters in Australia, not a full blanket sort of carbon pricing arrangement like in the EU. From that, there's also been a recent release of a carbon leakage report to government, and I guess a debate is now opening up around the use of CBAMs and what Australia might be able to do in that space. I've just come to my last slide, and I guess I just wanted to sort of put up, I guess, the 70 partners and growing membership of the HILT CRC. You will notice a new membership category down the bottom, international trading partners. So that's open to any international businesses that are customers of Australian producers. And our first one to sign up on that, it's been released this year, is POSCO. And we put the call out there and welcome any other people who want to join that free membership to get insight into the various project possibilities that can be done within HILT CRC. But thank you very much for all your time and look forward to the questions. Thanks, Alan.
Excellent. Thank you for that, Benji. Just in a small word of defence for that little tiny island off the bottom there, Tasmania is approximately the same size as Ireland, which means, for those who aren't aware, Australia is approximately the size of all of Europe. So on to our next speaker, please.
It's all
I'd love
relative.
to introduce to you, it is all relative, introduce you to Sven Schnuppner. Sven develops and implements technical assistance programs across more than 10 countries in Africa and the MENA region. He currently serves as the hydrogen expert at the United Nations Industrial Development Organization, as we know, UNIDO. Please, Sven, welcome. And your presentation title is UNIDO Hydrogen Partnerships in the Mediterranean.
Thanks very much, Alan. Good morning from Vienna, everyone. Very glad to see so many friends and partners here. My name is Sven Schnuppner, as Alan has said. I work at the United Nations Industrial Development Organization. And after Benji's exciting presentation on Australia, I'll be taking you back to the Europe and North Africa region, because we'll be zooming in on the Mediterranean with some learnings from the report that Zafer was mentioning in the beginning, zooming in on hydrogen hubs in the Mediterranean region and understanding how industrial development comes into play around hydrogen in the region. Maybe just briefly in the beginning, a quick reminder, for example, for the Australians who are not a member country of the United Nations Industrial Development Organization, of what our work is about. We were founded in 1966 and have a very strong mandate around SDG number 9, which focuses on industrial development, innovation, infrastructure, and or the core of our work is therefore around promoting and accelerating sustainable and inclusive industrial development. We've been hosting the Global Program for Hydrogen Industry since 2021. The Global Program is the UNIDO activity that I'm part of. And through the Global Program, we on the one hand have a strong focus, of course, globally, but with quite a presence as well in the Mediterranean region, where we support across many different topics with a strong focus on policy and regulation, knowledge products and publications, technical assistance projects with partner countries focusing on putting the right regulatory frameworks in place. We support COP presidencies, usually every year with the hydrogen declarations. We recently published a study on guidelines for sustainable hydrogen projects. Together with ISO, we work on standards and certification. Innovation plays a big part in our work. Inclusive trade as well. I'll be going a bit deeper into that later, because we have been co-hosting the International Hydrogen Trade Forum for a few years, and will soon be supporting the Southern Hydrogen Corridor connecting North Africa and Europe in the Mediterranean region. In more detail. And then I'll be speaking briefly about skills capacity development as well, because we'll be soon launching a skills assessment methodology that we piloted in Tunisia and in Egypt, trying to understand what are skills gaps and how can policymakers respond to these. From there, let's have a quick look at the Mediterranean, and the main argument that I'd like to make in this presentation. I think if you take away one thing, that should be this: if you look at regions or hydrogen hubs, or however you like to call sort of the geography that you're looking at, we believe that hydrogen hubs need anchor demand, and that hydrogen only scales through local industry, as well, of course, in addition to international off-takers. Headquartered in Europe, we oftentimes, in discussion with private sector and policymakers around us here, encounter the idea that sort of North Africa is seen as an export hub, with the offtake and the industrial application happening in Europe. And we have been arguing for a long time that a local industry and local offtake and application should be part of the picture, making the case for the fact that export-only strategies are politically fragile, they risk stranded assets, and they're of course quite subsidy dependent from funds where the off-takers will be located, in that case Europe. So therefore we believe that demand creation in the centers of production, so to speak, deserve equal attention to supply a ramp up, and therefore corridors such as the Southern Hydrogen Corridor connecting North Africa to Italy, but also ELMED for green electrons, an undersea cable connecting again North Africa to Europe, do require offtake on both sides, because what I took away from Piero's presentation earlier, and thank you very much for that, is on the one hand a slowing and also unbinding, non-binding offtake agreements that then also, and that's very much echoed with what we see in the project that we work with, is of course a struggle to reach FID. Projects do struggle to reach final investment decision, and we believe that a local offtake for these industries can be a key enabler. If we look now at the North African industry in a bit more detail, I picked out 3 sectors: steel, fertilizer, and chemicals. Fertilizer and chemicals, of course, quite related. Where I just wanted to put a few spotlights on sort of ongoing initiatives in North Africa, but also partially in Europe, to show where industry in these regions stands and where potentials are. I was putting Morocco currently through a Green Climate Fund Readiness Program to understand the potential of direct reduction iron in steel production, and we see a very dynamic, also already a low carbon steel sector in Morocco with very high potential and very strong interest in decarbonizing further, be that through increased integration of renewables, but also studying and introducing DRI, electric arc furnace assets, and sort of DRI ready steel facilities we find in Italy as well, of course. On the European side. For the fertilizer sector, we discuss with many of our partner countries the potential for substituting grey ammonia, which is imported in the cases of Tunisia and Morocco, for instance, with the domestic green ammonia production. So we do not just talk about greening the production, but substituting imports. And so there's a import substitution a debate going on in parallel, which we find quite interesting. Therefore, we're working in Morocco, for instance, with OCP, quite interested and committed to building out a domestic green ammonia value chain. Egypt, of course, in that sense, quite ahead as well, with H2 Global funded green ammonia offtake agreements in the Suez Canal region. And speaking about the Suez Canal region, chemicals, of course, in maritime transport hubs, such as green methanol, are very relevant options. I see Alan turn on his camera, so I'll just quickly jump through 3 UNIDO solutions. One of them is a publication that we launched recently. It's a replicable model for industrial clusters, something that we've been working on at UNIDO and now applying to hydrogen for a long time. I encourage you to check out that publication if you're interested in industrial synergies and how hydrogen can support those. The Southern Hydrogen Corridor Secretariat that I briefly mentioned earlier, where we will be supporting the political dialogue policy alignment, stakeholder coordination between the 5 countries, as well as observer states and the European Commission, where UNIDO will be providing a platform. And then speaking of platforms, I'll just close with an invitation to all of you to UNIDO's International Conference on Hydrogen Industry on April 8th, which we'll be hosting here in Vienna. It's a invitation-only event, but please do feel free to reach out and request your invitation if you're interested in joining the session. It's a one-day conference, and it's followed by the International Vienna Energy and Climate Forum, another very exciting energy conference happening here in Vienna. And my contact details you find on this last slide here, and all events upcoming and past you can find on our LinkedIn page, UNIDO Hydrogen. Thanks very much.
Excellent. Thank you, Sven. And don't worry, you're almost perfectly on time. Remember, questions into the chat, please. We will get to those at our Q&A session at the end. But it's my pleasure now to introduce our next speaker, Margarita Matza. Margarita is the project manager of Austria's first hydrogen valley, the Hydrogen Industrial Inland Valley in Austria, or HI2. The HI2 Valley was launched at the beginning of 2025 and is funded by the Clean Hydrogen Partnership. It is my pleasure to introduce you to Margarita Matza. Over to you.
Thank you. And hello, everyone, from my side. I will jump right into the part. I am Margarita Matza, and I'm from WIFA PNG. WIFA PNG is a research association who has a network of hydrogen and other climate-neutral gases all over Austria, transregional and thematically focused. We started in 2019 as a flagship region funded from the Austrian government, where we really had the projects along the whole value chain, all in all around 30 ongoing or completed projects at the moment. And these are multidisciplinary projects where we try to implement an innovation structure. And the goal is, of course, to support the transition to a sustainable energy system. When I say we are association, we need members. You see here our members. We have 19 industrial members and 7 research members, and these are all over Austria. We have, when we already said, we think about the whole value chain. So the idea of our project were to have a project which is focused on production, a project which is focused on storage, underground storage, a big possibility in Austria. Project 2 is then focused on industry, another one on the distribution, and then on mobility, and so on, and all in all to build as a flagship region, the flagship region Austria, a whole valley, which actually is already what's going on now, but the idea we had already back then. So here you see a map of our already really built projects we have in Austria under WIFA PNG. So you see it's all over Austria, and we have electrolyzers, mobility, we have the industry, storage all included. And maybe you see slightly here in Upper Austria, Carinthia, Styria, Carinthia, it's a little bit darker because here it's the Hydrogen Industrial Inland Valley, which I am leading. After all this work we started in 2019, we decided, okay, we already have the idea of a valley. We should also apply for a valley and call it a valley. And so this 3 region, which there were a lot of the projects ongoing already, the flagship region, we decided to put together as a valley. So we built the Hydrogen Industrial Inland Valley. It's a valley with nearly 600 million euros budget. 20 million we get from the EU for the Clean Hydrogen Partnership. We have 44 partners and will install around 100 megawatt electrolyzer. So this 100 megawatt electrolyzers give us 10,000 tons hydrogen, climate neutral hydrogen per year. This all is planned for 6 years. We are already in the second year. The idea is to have this in 3 steps. The first 2 years is the planning phase. So at the moment, 2 projects are really already in the operation part. The others are still in the planning phase. So some of the project will also change. Anyway, after 2 years, the project should start the deployment, and then we have 2 years at the end for the operation part. Why are we together as a Hydrogen Valley? What do we want to do beside these projects? We want to strengthen the entire hydrogen value chain, of course, with the production storage and the distribution at the end use. And the distribution is about industry, of course, with the Hydrogen Industrial Industry Valley, but also mobility and energy. And then we have this all connected with a pipeline, and to really then have the distribution going over the pipeline Austria. That's why we have also the pipeline provider in our valley included as a partner. You can see here the partners, because I talked about 44 partners. Of course, I am leading it, but it's not me doing the work. And we have these partners from Austria, but also from all over the world, all over Europe, be honest. Yeah. So you see there the big range. The 70 projects we really want to put in place are in Upper Austria, Styria, and Carinthia, at the different location all over this part. On the next slide, you can see it a little bit more detail, even if I have to say some of them will change. So it's not exactly how it will be, but you see we have production, we have storage, we have HRS implants, we have industry. So all together they are connected via pipeline, mostly the hydrogen backbone at the end, but also with the trailer decision. Yeah, and I think I'm the one who is good on time because I don't need my 9 minutes. I have the idea is what's on the next step. On the one time, I already told you the idea of the valley, that we are this 3 steps. So you know, come like, why is it not built? It's a marathon. We can rush through it, but we have these projects already ongoing. But that's not all Austria want to do. We have further projects in the pipeline, and also one further Hydrogen Valley would like to have. That's the High Hope, if it's in Austria, in the region of Vienna and Lower Austria, Burgenland, together with Slovakia and Hungary. They have they work quite well, and I think that should be the next valley in Austria. Then we have in the west, we have the Brenner Valley, which is at the moment in exploration talks, so we will see what's going on there. But also here we have the part that we have Bavaria, Austria, and the northern part of Italy together, because Austria is a country in the center of Europe. So in our case, we are, for the Hydrogen Industrial Inland Valley, we are focused in Austria, simply it is in the middle, but for the other parts as well, for the east and the west, as a center of Europe, it only makes sense to cooperate with other countries, and that's why we are happy to have this collaboration and the other projects. And with this, I'm already at the end of my happy to get in contact, happy if you visit our site at Viva PNG, as well as at the Hydrogen Valley, as well to see you on LinkedIn. So thank you.
Thank you very much, Margarita. I will have a question for you, but we'll save that one for the Q&A session. Our next presentation is from Dr. Patrick Fortin from CETP. Patrick is a senior research scientist in the Department of Sustainable Energy Technologies at CETP, where he leads research efforts in the development and characterization of advanced materials for hydrogen technologies. His presentation today is Progress Towards High Performance, Durable and Low Cost PEM Electrolysis. So I'm pleased to introduce to you Dr. Patrick Fortin.
Thanks, Alan. Good morning, everybody. Yeah, so I'll be talking to you guys today about some of the progress we've been making in our labs towards high performance, durable, low cost PEM electrolysis. And so the results that I'm going to be showing are all part of the Unicorn project. So this was a project granted in the very first call of the CETP partnership back in 2022. So the project started November of 2023 and it's slated to finish later this year. So it's a collaborative project between universities, research institutions, and industry partners, with the main focus on developing new components for electrolyzer stacks that are going to lead to reduce capital costs of the stack. We want to increase performance of the stacks, increase the sustainability of the components, all while maintaining the durability target. So it's going to be a bit more of a technical talk than we've seen so far, but I'll do my best to keep it more a general overview without delving too far into the technical side of things. So with respect to reducing the cost of the PEM water electrolyzer stacks, the main driver is the use of platinum-coated titanium everywhere in the stack. So you can see sort of this blown out diagram of what our, at least this is a single cell electrolyzer, looks like. We have platinum-coated titanium flow fields, current collectors, porous transfer layers. There's this platinum-coated titanium everywhere. And when you look at the cost breakdown of the stack, 50%, almost half that, or more than half that stack cost is from the bipolar plates or the flow fields, because there's so much platinum coated titanium. So the question that we wanted to ask ourselves was, can we use alternative low cost materials to produce bipolar plates and maintain that same performance and durability as the state-of-the-art platinum coated titanium components? And so this is where our partner Alema comes in. They're a Swedish steel manufacturer, and they make carbon-coated stainless steel bipolar plates at commercial scale using a continuous physical vapor deposition procedure. And you can see here, one of the most important characteristics or measurements is the interfacial contact resistance. So that's going to tell you the electrical resistance at the interface between the bipolar plate and the porous transport layer, and that's important to have efficient electrical conductivity through your system. And you can see in this sort of burgundy line here is the uncoated stainless steel. The interfacial contact resistance is just much too high to be for practical use in an electrolyzer. But after Alema puts on their carbon coating, that's this Synergy in sort of salmon, it's well below this DOE target of 10 milliohm centimeter square. So it has enough conductivity to be practical, and it performs similarly to a gold coated bipolar plate. So we wanted to see how these look in an electrolyzer at Syntef, so we put them in there, did some polarization curves. So this is sort of a global view of performance, the polarization curve. The goal is to have as high of current density as possible with the lowest potential as possible. So you really want this curve to be as flat as possible. So we did some electrolyzer tests with the state-of-the-art platinum-coated titanium components, platinum-coated titanium PTL and flow field. We use flow field is the nomenclature that we use in a single cell bipolar plate, is what we would say for a stack. But for this presentation, if you see flow field or bipolar plate, just know they're equivalent. They're the same thing for all intents and purposes here. And then in the orange line, we've now used our carbon-coated stainless steel flow field and also PTL. We don't have enough time today to get into the PTL development, but we are also developing PTLs that reduce the amount of platinum titanium. So we're really trying to move away from platinum-coated titanium everywhere in the cell. And you can see performance is a little bit lower in orange, but performance is still comparable and still good. We're at 4 amps per centimeter square, just above 1.8 volts. So we're happy with that performance. And more importantly, we've shown that that carbon coating survives the beginning of life characterization protocols. So how does that look for our CapEx then? So we set our goals based on the Clean Hydrogen Joint Undertaking, SRIA. The 2030 KPIs is what we've been using. Even though the project ends in 2026, we wanted to be sufficiently ambitious with our targets, and we think we can reach some of these targets. So we're sitting right now at about 860 euros per kilowatt at the system level. So these targets are all system level. You'll see here, just ignore the yellow one for now. We've included EPC costs in our techno-economic analysis. The three kind of stop at the top of these gray bars here. And you can see the biggest driver here is in the CapEx reduction is the stack. We've reduced stack cost by almost half by implementing these carbon-coated stainless steel as opposed to the expensive platinum-coated titanium. Orange and gray bars, the power electronics VOP, these will not change in our project. We're not doing any innovations there. This is exclusively a stack component development project. So with further innovations there, we can even drop this further, but stack 50% less, that's great. The second major innovation in the Unicorn project is the implementation of this vapor-fed anode operation mode. So in a traditional electrolyzer, what you'll see is water is fed at the anode. It's then oxidized to produce oxygen and protons. Protons make their way through the membrane where they're reduced to produce hydrogen. Now, hydrogen crossover is a concern. If hydrogen crosses over into your anode feed, hydrogen and oxygen, you can get an explosive mixture. So you have to use a sufficiently thick membrane to prevent hydrogen from crossing over. In this high star configuration where we're feeding humidified air at the anode instead, and we've now moved that water feed to the cathode side, what happens is that any hydrogen crossing over is diluted by this air. So you no longer have any hydrogen crossover concerns. You have no explosive mixture because everything is diluted from this air. This allows us to use a much thinner membrane. We're using an 18 micron membrane versus typically 127 microns, NAFI 115, if anybody's familiar. And so this thinner membrane really reduces the ohmic resistance significantly, and this leads to greatly increased performance and electrical efficiencies of the stack. So when we look at sort of the performance targets now, the current density is one of them. So looking at nominal operating current densities, the goal 2030 goal is 3.25 amps per centimeter square, and we've already surpassed that. These are the polarization curves. You can see we're sitting at 3.5 amps, less than 1.8 volts. So that's great. Performance is really high in these vapor-fed electrolyzers. We can use the same data to look at our platinum group metal loading. So this is one of the things that is going to also reduce cost if we can maximize the utilization of our catalysts. These are the loadings that we're using. This is sort of the industry standard right now in a commercial PEM electrolyzer. We've set our target to 0.3 milligrams per watt using 2 mgs of iridium per centimeter square at the anode and 0.8 milligrams of platinum per centimeter square at the cathode. We're able to achieve 0.43 milligrams per watt right now. So on our way down to the target goal, but not quite there yet. So we're going to work on that this year. Finally, looking at degradation, how durable are these components? So we've demonstrated 500 hours of operation with these carbon-coated stainless steel components in the electrolyzer cell. So we run 500 hours of constant current density operation, 3.5 amps per centimeter square, and 80 degrees. So this is higher than most things that you'll see out there in the literature. And we see here that our degradation is actually significant. It's 3 times higher than our goal. But so two things to point out. This is fairly harsh in terms of current density hold, constant current holds, and degradation is always overestimated at the beginning of life. This initial degradation rate is always high, and you can see when we stack the polarization curves over top of one another, the gap between this blue curve and the orange curve is much bigger than the gap between the red and the brown curve, which are almost indiscernible. So first 5 days, you see a lot more performance degradation than in the last 5 days. And this is true in general of these electrolyzer systems. And electrolyzer manufacturers will often exclude the first 500 to 1,000 hours because of this break-in period where we see this degradation. So I'm confident that if we extended our durability, so this time on the x-axis, if we extend this out to 1,000 hours and take the last 500, our numbers would be much closer to our target. So that's something that we want to do towards the end of the year. So in summary, we've demonstrated that carbon-coated stainless steel bipolar plates may be a viable alternative to the expensive platinum-coated titanium. And we've shown that the vapor-fed anode operation provides significantly increased performance and efficiencies. One of the main things in the project is also to replace these PFAS-based membranes with hydrocarbon membranes from our Canadian supplier Ionomer Innovations. That's ongoing as we speak. We want to reduce the iridium loadings by 50% at the anode. That's going to help us reach our PGM loading targets and also long-term durability of the unicorn stack. Everything's been done at single cell so far, so we want to put this into a stack and show that this works in sort of a commercial scale. So with that, I'd like to thank you all for your attention, and I look forward to answering any questions you may have. Thank you.
Excellent. Thank you very much for that, Patrick. We won't do the questions until after our final speaker, who I'm pleased to introduce is Volker Schulman. He's the Head of Technology and IP for Hybrid Development AB Bio. Volker has been deeply involved in building up and running the Hybrid Pilot Scale Development Program between 2018 and 2024. Today, he's responsible for technology and intellectual property within the Hybrid joint venture company. Pleased to hand over to you, Volker.
Thank you so much for the invitation and the introduction, Alan. I'm representing here the hybrid team in order to the project team that has been developing and scaling up a technology for underground storage of hydrogen as a support to realizing a fossil-free iron and steel value chain that we're working on. Give you a short reminder, and let me see whether I can change the slide here. A short reminder about what the hybrid is about and the initiative. It was started in 2016, and it is about eliminating CO2 emissions, fossil emissions from the iron and steel industry. It's a joint venture and initiative between SSAB, a steel company, LKAB, a mining company, and Vattenfall, an energy company. The work has been supported by the Energy Agency here in Sweden and the European Union as well, I should mention. So how to eliminate, short reminder on how to eliminate CO2 emissions when it comes to iron and steel. Here is a short snapshot of the value chain that we're working to implement. So it is about starting from iron ore, working with a fossil-free induration pelletization process, followed by a hydrogen-based direct reduction process, thereby followed by a melting step here in the form of an electric arc furnace. The entire focus has been using and developing technologies from a stage that are considered suitable to achieving the transition and enabling the transformation to a fossil-free value chain. And so we've been focusing since 2018 a number of pilot scale development projects to work in a simulated industrial environment where we have all the features of an industrial scale process, but at the same time the flexibility to develop. So we've been running this program for the length of about 6 years. It has been very successful, and we've been identifying in overall the industrial feasibility and have been handing over then these results in order to enable the next step and scale up to industrial scale. Today, I want to share some information about our work on a hydrogen storage. We've been running these different efforts regarding the different process steps in parallel, and I want to talk a little bit about how the integration with an electricity system and the supply of hydrogen, how this is addressed and how we've been working with this. So what is the type of challenge we're looking at? So if running a fossil-free hydrogen-based direct reduction process, it requires large amount of electricity and hydrogen. And this is then playing in the context of an electricity system that everybody is aware of and is discussed quite a lot in different places now in view of this transition. So there is a varying supply and demand in electricity system, and these fluctuations, they occur on different time scales during the day, during a week, and during the different seasons. The electricity is, of course, used then for electrolysis of water in order to produce the hydrogen. And this, as a result, and these variations in supply and demand, they lead to price variations. And they are expected to develop as the source of energy production is going to include more and more intermittent energy. energy sources such as wind and solar. So how to handle this then? Our proposal and the way that we've been addressing is to use hydrogen storage to manage these fluctuations and to take advantage of them. This may be pretty straightforward, but here's a slide to shortly illustrate on how to do this, how to take advantage of these fluctuations and how to manage this and take help of it in order to integrate it with the electricity system. You see here a schematic value chain where we've got a large-scale hydrogen storage, which is connected via a pipeline to an industry, to a direct reduction plant here. And we've got here at the center an electrolyzer, which is producing hydrogen. Now we're here symbolizing here a situation of abundant supply of electricity, which is corresponding to quite low electricity prices. So now we are able here to supply continuously the direct reduction plant with hydrogen. And at the same time, we can produce hydrogen in order to store it in our hydrogen storage. So by investing into a hydrogen storage and into some overcapacity, we can produce in this situation extra hydrogen. We can store it here. So we create flexibility whilst at the same time securing a continuous supply of hydrogen to the plant. So what's happened then if you go to a situation with a high electricity demand and high electricity prices? Then you've got now the flexibility in order to reduce the hydrogen consumption here, or the hydrogen production, I want to say here. And instead you consume hydrogen from the storage, which is then used to the direct reduction plant in this case. This flexibility has got the positive effect both on how to on the price, on the variable cost of hydrogen production, but it's also positive as to how to the electricity system. So it's a symbiotic effect here. So how do we go about to implement and realize this in the hybrid initiative? We've been based on our analysis of the situation in the north of Sweden. We've been analyzing a number of different storage technologies, and we have identified for the conditions here in the north of Europe, the LRC technology as the most advantageous technology. LRC stands for lined rock caverns, and I will just explain in a minute what this is about. In this project, which we've been running for about 5 years, we've been using an existing technology for storage of natural gas in large quantities. And we've been adopting the technology for the use of hydrogen and for the use case to support the fossil-free value chain for iron and steel. So we've been developing a pilot-scale storage facility. We've been designing it. And then we've been testing it, and we've been actually testing it also in integration with the electricity system as well as with off-takers. Here a slide now to describe a little bit more what the lined rock cavern is about. So it consists basically of a rock cavern here and an access hole that is symbolized here. And the gas is contained in a liner, and which is in a very simplified way now here, this white line here. And the pressure, the high pressure when we are storing the hydrogen, that is absorbed here by the rock surrounding it. The pilot plant that we've been building is located in the north of Sweden in Luleå. It's about 30 meters deep under the surface, and it has got the size of 100 cubic meters. It's filled to about 250 bars. It can be filled to a maximum pressure of about 250 bars. And that corresponds then to approximately storing 100 megawatt hours of energy and about 2 tons of hydrogen. So just to give you a glimpse of our results, I want to show you some KPIs. We've been successfully testing the technology under many hours of operation. We've been verifying its tightness. There is no leakage occurring throughout the entire test period. We've been able to demonstrate 2 tons of storage of hydrogen inside the plant. And we've been doing some accelerated lifetime testing of the plant. So in total about 50 years. So the performance has been really valuable and has been impressive. So we've been showing the integration with both with off-takers as well as with the electricity systems, and demonstrating then that we can reduce the variable cost of hydrogen production by about 25 to 31%. I come to a final summary slide here. We've been establishing with this development project that the hydrogen storage can support the transition to a fossil-free society. It generates a number of benefits. We've been able to show and demonstrate in pilot scale that it allows us to lower the variable operating cost of hydrogen production. It creates the flexibility and the stability for continuous supply for industrial operations. And at the same time, it is very beneficial for the electricity system. It is enhancing grid stability, and it's reducing price fluctuations in the electricity market. I'd like to stop here and look forward to your questions and taking a dialogue.
Excellent. Thank you for that, Volker. We will have to shorten our question and answer time to make sure we do finish on time today, out of respect for all of our guests. I will start with at least one question for each speaker, starting with Piero Venturi, if I could, please. Piero, what are the priority industrial sectors that the Clean Hydrogen Mission will focus on in 2026?
Okay, thanks. Thanks. I put my camera like this. Well, we have basically three priority sectors. The hard-to-abate transport sectors, I already mentioned, maritime, aviation, mining. Then hard-to-abate industries, such as refining, chemicals and metals, and the long-term energy storage and dispatchable power generation. That's it. Short.
Excellent, thank you. Short and sharp. And if all of our speakers could keep their answers short and sharp, we'll get through more questions. So that would be much appreciated. Second question, please, to Benji Lee. The policies you described for Australia, are they starting to have an impact in terms of heavy industry decarbonisation and hydrogen projects and the investments that are being made?
It's slow going, and I guess this is there's been a flurry of, I guess, policy development, with the second round of hydrogen head start, and then all these industrial sort of policies on top of that. So it's still a little bit early to tell. Really what they're wanting to do on the hydrogen side is get price discovery around what is the gap, and can they get some bigger projects moving. But like I said, it's sort of, that the projects being built are just, around the 10 megawatts, a few, 2.5 megawatts. So this next round of policy, is wanting to, I guess, up the ante on that, and we'll see. The submissions have gone into the Hydrogen Head Start Fund, so that will be a very interesting process when that selections sort of occur later in the year.
Excellent, thank you, Benji. One thing's for sure is industrial decarbonisation is a very long game, and managing those public perceptions of how long it's actually going to take is part of our challenge. My next question, please, to Sven. What are some concrete examples of partnerships or technical assistance through which UNIDO is supporting hydrogen development in that Mediterranean region?
Yeah, thanks, Alan. I mean, as I said, the Mediterranean region is so particularly important to us. And, as a technical assistance organization, of course, we do your trainings. We do policy work with decision makers and private sector as well. We recently completed a pre-feasibility study for steel decarbonization and DRI introduction in Morocco. So we work very much on that front. Also published the decarbonization roadmap for steel and cement industry in Morocco. And then at UNIDO, of course, we can work quite closely with the private sector. We recently concluded an MOU with OCP on decarbonization. Regularly speak to the import alliances across Europe for hydrogen. So it's a nice interface as well, nice place to be in between private sector and government.
Excellent, thank you. Just a note for everyone, we may not get through all of the questions that are in the chat, but we will make an attempt to get an answer to everyone from our speakers if we don't get them addressed here in the live webinar. My next question, please, is for Margarita. What is being done in Austria to establish a hydrogen gas network?
Yeah, because in Austria, it's quite, as I mentioned in my presentation, that we are working and fixing that we already counting with the hydrogen network. But of course, it is a long story going on. At the one side, in Austria, they are quite active to working on the hydrogen backbone, but also the different levels of the pressure network we are going on. At the moment, there is from AGGM, a questionnaire for everyone who will use hydrogen in Austria that they should fill it out. So everyone is here from Austria. Maybe I can send you, I will send the link in the chat in a minute to fill out this one, because then we know where to use it. That's the one thing. And the other thing is that there's a discussion going on if to start at the beginning, we could also make a blending into the gas network and then have the pure hydrogen network. So it's a ongoing discussion, which is quite often urgent for Austria, that the industry can go on and that the hydrogen economy has a chance. So that's one key role we have to work on.
Excellent. Thank you, Margarita. The next question I have here is for Patrick. You mentioned that you're developing PTLs in the project. Can you provide some more details quickly on the types of PTLs that you're developing?
Yeah, absolutely. So sticking with the same theme as the bipolar plates, we're replacing a large majority of the titanium with stainless steel and some of the platinum coatings with carbon. So we start with a woven stainless steel substrate. And unfortunately, we haven't found a good way to get completely away from titanium platinum right in contact with the catalyst layer. So we put a thin thermally sprayed titanium powder coating on there and another thin 20 nanometer platinum coating. But on the back side, we've now completely removed the platinum coating with the carbon. So again, working towards replacing titanium and platinum with stainless steel and carbons that are much cheaper.
Excellent. Thank you for that. Volker, if I could ask you a question as well, please. How do you ensure that those lined rock caverns, LRCs, how do you ensure the technology is a safe method to store the hydrogen to avoid risks with leakage, explosions, especially when you're dealing with such high pressures?
The safety has been focus area throughout the entire project. So I think it's been a key aspect. So we've been doing extensive tests and a validation of the entire steel liner that we're utilizing, and even other supporting barriers like concrete, to ensure that they can withstand the high pressures and prevent the leakage. In addition, then we've included several advanced safety systems in order to be able to detect and to manage any potential leaks. And so we haven't identified any leaks, so this has worked out quite well. And then, of course, everybody knows about hydrogen corrosiveness and corrosion. So the material selection has been a key aspect for the steel liner, and also the other quality controls in general are quite important for the entire design. Thank you.
Excellent. Thank you for that. I think we're only going to have time for 2 more questions in the live webinar, but as I said, we will try and address people's questions in the chat in what we can send out to all of our guests today. So second last question to Piero from Fatima. There are claims that electricity for electrolyzers used in green hydrogen production will be subsidized. Is this accurate? And to what extent are those subsidies going to help bridge the cost gap?
Okay, here I am. Well, so it could happen that some are subsidized, but nevertheless, a cost will remain very, very high. We all know that to have cost-efficient hydrogen, the best solution is to produce it from electrolysis in regions with very favorable solar and wind conditions. So let's think about what is happening in Australia, in Chile, in Namibia, and this with the aim to ensure cheap electricity and, well, in this way to have cheap hydrogen.
Excellent. Thank you for that. And what is possibly the last question that we're going to have time for? This question is to Patrick. Again, sorry, it's also from Fatima. Could you express your achieved efficiency in terms of electricity to hydrogen conversion efficiency in percentage, roughly?
Well, we haven't calculated that yet.
That's okay. That's a very simple and quick answer. Okay. On that, we only have a few minutes left in our presentation. I would like to thank all of our speakers, but I would like to introduce, for a wrap-up, to reintroduce you to Urban Piker, the Mission Director from the Net Zero Industries Mission, for a quick closing summary. And please remember, we will be trying to answer all of those questions we have not managed to get those answers to you later. Urban, over to you.
Thanks, Alan, and thanks for the opportunity to close today's webinar. Thanks, Alan. Thanks for moderating us through today's webinar in such a smooth and pleasant way. Let me offer a brief personal wrap-up of this inspiring session. Hydrogen plays a critical role in achieving long-term climate targets. And obviously, there's still quite a way to go, as 99% of hydrogen is still produced from fossil fuels. Piero provided a very important reality check at the beginning of this session. And obviously, we need to further expand renewable production capacity. And this means a variety of sectors to look at: skilled labor, supportive regulation, stronger demand creation, and particularly this through large-scale demonstration projects. Innovation is key, and we had an interesting glimpse into activities and policies in Australia, but as well a glimpse into industrial hubs and future trade routes in the MENA region. Hydrogen valleys could provide a blueprint as an enabling ecosystem to scale up solutions, as we have seen from the example of Austria. And for the last two presentations, green hydrogen is advancing through innovations in many different ways. Research institutions such as CETP, together with their consortium, is developing more sustainable materials to reduce reliance on critical components. And what we learned today quite impressively is that this is very important, as cutting costs is very important to kick us off here. PEM electrolysis is just one example. And in heavy industry, steel production remains a major emission source. Hybrid is actually at the moment working at fossil-free value chains there and looking particularly into hydrogen storage, which is very important to introduce a new level for flexibility. And this is as well one level to reduce costs again. So in a nutshell, it's a very dynamic technological progress here, and at the same time, systematic and systemic challenges involved in scaling hydrogen solutions across energy and industrial sectors remain quite big. The road to net zero is complex, we all know that. Nevertheless, or even more importantly, collaboration and shared knowledge along the hydrogen value chain remains essential to make this achievable. And at this point, I would like to really thank all the speakers for sharing insights about the incredible work you're all doing and for your input in today's discussion. And thanks a lot to all the attendees for the questions. We hope that today's session has sparked a few further ideas and further strengthened trust in the potential of the presented technologies. Thank you once again, and we're looking forward to continuing this important journey with you until next time, which is, if you're interested in carbon capture and utilization in general, and in CO2 mineralization in particular, that next meeting could be in the course of our next webinar, which is planned for end March, beginning of April this year. So thanks a lot for joining, and goodbye for now from my side.
Excellent. Thank you, Irvin. A special thanks to our partners, being the CETP and Alliance for Industry Decarbonisation, and of course our sister mission, the Clean Hydrogen Mission. Thanks very much to the AIT team behind the scenes who organised this, especially Irmgard and Oksana and Katrin. But thank you all as participants. Please note that a recording of this webinar will be available on our YouTube channel and accessed via the Net Zero Industries website. The links for those are in the chat. We will try to get back to you with questions that we didn't get time to answer during that time. And please check out our events page to actually tell you when the next webinars will be held. With that, thank you all. Have a very good day, a very good evening, and we hope to see you again next time. Good night.
Thanks. Bye, everyone.